So describe the conditions required for an object to perform simple harmonic motion. That's our first thing, right? Okay. Remember that the rules are that you've got what, an equilibrium position, and that the force is toward equilibrium and proportional to the displacement. So if you double the displacement, you'll double the force, and it's toward the equilibrium. But by the way, also, don't you have to be moving, either moving or displaced from equilibrium to begin with? I feel like they never mention that, but these are the conditions, right? Okay. Okay, so let's see. A 0.52 kilogram mass performs simple harmonic motion with a period of 0.86 seconds when attached to the spring. Okay. The wooden block attached to the same spring oscillates with a period of 0.74. Okay, the period of this thing is going to be 2 pi square root of m over k. And they're saying that 0.86 equals 2 pi square root of m over k, and the mass is 0.52, sorry. All right, okay. Can't you solve that for k? So solve for k. I mean, there's other ways to do this, right? But this would be a real concrete way to do it. Solve for k. And then they say a wooden block attached oscillates with a period of 0.74. So now you can go 0.74 is 2 pi square root of the mass of the block, right? Over whatever that answer is that you got, right? You solve for that, put that answer in there. And you ought to be able to solve for the mass of the block. The mass that I got was slightly less than 0.4 kilograms, that I'll tell you, okay? There's lots of ways to do that. I set up a proportion or something like that, but maybe people find that confusing, okay? In carrying out the experiment, a student displaced the block horizontally by 4.8 centimeters from the equilibrium position. Determine the total energy in the oscillation of the wooden block. 2 ways to do this, okay? Way number 1 is we're assuming that they release it from rest at 0.048 meters, right? So way number 1 is you can say the total energy is just the potential energy that it starts with. So that's 1/2 k that you figured out from here times 0.048. I never figured out k, by the way. I'm just saying, but you could do it this way, right? So this is just 1/2 kx squared. You could also do this too. The total energy is 1/2 m omega squared x naught squared, right? X naught squared is this, right? 0.048 meters. Omega is going to be 2 pi over, what's our period? 0.74. And the mass is what you figured out from here. Either way, you're going to use something that you calculated, either the k that you calculated from here or the mass that you calculated from there. I suspect they want us to do this, but this is exactly the same thing, okay? All right, let's see, what's the next thing? Oh, I think that's it for us. Yeah.